All right, so this is the second part of our lesson on inverse functions. So we learned that there's 4 steps we can use to find the inverse of a function. Now, again, don't forget on each of these we need to determine whether the function is one-to-one. Now you can certainly graph number 7. We've done that previously. But if you want, I would be comfortable with you putting it into your calculator. So, these take a little bit of time. We're just going to go ahead and put it in the graphing calculator, and I would use the Zoom standard window. And when you do that, you'll see that this does pass the horizontal line test, and so it is one-to-one. So let's go through the steps. Now this one's going to be a little bit harder than the ones we did before. Let's replace f of x with y, and let's switch the x and the y. So now we need to solve for y. So we've got a few steps of algebra to do here. So first of all, when I have fractions in an equation, normally I want to clear those first. So let's go ahead and do that. Our LCD is y plus 7, so we're multiplying each side by y plus 7. On the left, we're going to have to distribute. We get xy plus 7x. On the right, our y plus 7s are going to cancel, and we're left with 4. Now remember what we were trying to do. We need to solve for y. That means I want to get rid of the 7x term next. So I get xy is equal to 4 minus 7x. And finally, to solve for y, I need to divide by x. And so we're going to get 4 minus 7x all over x. Now don't forget, we need to change back to the function notation. All right. Let's move on to number 8. So again, it says determine whether the function's one-to-one. We know how to graph this one. This is a parabola. Notice it's going to be a vertical shift down 3. And because of this 2 there, we're going to have a vertical stretch. So it's going to look a little more narrow, and it's going to look like that. It's down 3. So we have a problem here. This does not pass the horizontal line test. This is not a one-to-one function. Now we're going to actually change the problem so that we can find the inverse. And this is how we do it with a situation like this. So basically, I'm going to get rid of the left side. And what I'm going to do, really, to do that is to limit my domain to when x is greater or equal to 0. And so we're only using or looking at the part of the graph that's greater or equal to 0. So notice it does pass the vertical line test now. And so this is one-to-one now that we have that restriction. So let's go ahead and replace g of x with y. Now I'm going to go ahead and write my restriction here because we're going to need it when we switch our x's and our y's. So let's go ahead and do that. We get x equals 2y squared minus 3. Now remember that our domain for the original function is going to be the range of the inverse. And so here I would have y is greater or equal to 0. So now I need to solve for y, so I've got some work to do. I need to add 3 to both sides first. I get x plus 3 is equal to 2y squared. And now I'm trying to get to just y. I need to get rid of the 2 next, so I'll divide both sides by 2. I get y squared equals x plus 3 over 2. Now I'm going to go ahead and switch sides. And if I want to solve for y, I need to get rid of the square there, or the exponent of 2. The opposite of squaring is taking a square root. The only problem is I got to do that plus or minus thing. So I'm going to get y equals plus or minus the square root of x plus 3 all over 2. Now, but remember, we said y is greater or equal to 0. So what that tells me is I can't have the negative here. I'm just going to have the positive case, since we restricted ourselves to y being greater or equal to 0 when we flipped our x's and our y's. All right, so that's how you do a problem where you have a restricted domain. Now, number 9 is actually the one that's the most challenging problem. Number 7, you definitely could see something like that on the test. A problem like number 9, if I put something like that on the test, it'd be more likely to be extra credit. But you will see one of these in the homework, so I would encourage you to try this, and then you could look at my solution. All right, so first of all, this is your answer, or this is the answer. Hopefully that's what you got. So let's find out how I got that. So honestly, it really just comes down to the fact there's a lot of algebra, and it's all stuff that we've done, but we're doing it all in one place here. We actually did something like this when we were doing composition of functions. So let's go ahead and replace h of x with y, and let's switch our x's and y's. Notice we replaced both x's with y's. And so solving for y here is going to take some work. So again, I've got a fraction. I really want to clear the fractions. Our LCD is y minus 3. So let's go ahead and multiply each side by y minus 3. On the left, we get xy minus 3x. On the right, our y minus 3's cancel, and we're left with y plus 4. So we actually still have a fair amount of work to do here. You cannot solve for y right now because y is on both sides. So what I need to do is get y on the same side. This minus 3x term I really don't want on the left. So here's what I'm going to do. I'll go ahead and subtract y on both sides. Doesn't matter the order I put it in. I'm going to write it as xy minus 3x is equal to 4. And I just want my y terms on the left, so I'm also adding 3x to both sides. You get xy minus y is equal to 3x plus 4. Now, sometimes students get stuck here. How do I get the y by itself? These are not like terms. I can't combine them together. Factoring is what we need to do here. You can factor out a GCF of y. Y times x is xy, and y times a minus 1 gives you the minus y. On the other side, you still have x plus 4. So now I can divide, to get y by itself, I can divide by x minus 1. So when I cancel my x minus 1's, I get 3x plus 4 over x minus 1. And the only thing left to do is to change it to function form. All right, let's go ahead and move on to the next problem here. It says, find the inverse of the function by thinking of the operations of the function and then reversing them. Now, with more basic types of functions, we can do this. A problem like the one we just did would be quite difficult to reason out. But let me show you how you would do this. So on letter A, the function f takes an input, and the first thing it does is it adds 5 to your input, so x plus 5, because your input is x, and then you divide by 4. So whenever you start with an inverse, or whenever you plug in an input, you're going to add 5 and then divide by 4. Excuse me. So basically what we need to do is we're going to do the opposite operations in the opposite order. So the last thing we did was divide by 4. So the inverse, we're going to start by taking our input, or x, and multiplying by 4. Whoops, I did that wrong. Hold on a second. So the last thing we did was divide by 4. We're going to take our x and multiply by 4. And then the last thing we did, or I should say the first thing we had done is add 5, so we're going to subtract 5 here. All right, so my answer is going to be wrong here. I got to, actually that part didn't come out too bad. So again, if you look at the original function, it takes an input and adds 5 and then divides by 4. To reverse that, we're going to do the operations in reverse order, and we're going to do the opposite operation. So we'll divide by 4. Well, instead of dividing by 4, we'll multiply by 4 first, and then we'll do the opposite of adding 5. We'll subtract 5. Go ahead and see if you can do B. All right, so the first thing this function g does is it takes the cube root of your input. So we're plugging in x, and the first thing this function does, it takes the cube root of x. And then it subtracts 1. So we need to do the opposite operations in the opposite order. And so when we write our inverse, we're going to take x, and instead of subtracting 1, we're going to add 1. And then instead of taking the cube root, we'll do the opposite of that and cube. All right. So finally, last thing here, it's got a definition of the inverse. It says if a function is 1-to-1, then f inverse is the unique function such that each of the following is true. So I know this looks complicated. It's f inverse of f, or the composition of f inverse with f of x, is equal to f inverse of f of x, which is equal to x for each x in the domain of f. Now remember, composition of functions, we did this a while back. We said f of g of x is equal to f of g of x. So basically, g of x is the inner function. In the one we just did, this is f inverse of f of x. And so our inner function is f of x. And you can see down below it's the same thing. We're just going in the opposite order. So what's going on here? Notice our input is x. I'm sorry, I said that wrong. Our input is x, and our output is x. And that's true in both cases here. So what that tells me is when I compose these functions back to back, I end up with the same value that I started with. That's like what we were doing when we first started the lesson in the first video. It's this idea of these functions undo one another. So I'm going to write this down. Notice that the input and the output are the same. They're both x. Inverse functions undo one another. So basically, you plug in a value, you put it into the inverse function on this first one here, and then you get an output, and you plug that into f inverse, and what you get back out is what you started with as an input. So your input and your output are the same. So this is that whole idea of two functions undoing one another. All right. Now, these last two problems I know are a little bit, the work's kind of tedious, but there's some good algebra in here, and you need to be comfortable working with composition of functions. So this is some really good practice for that. It says for each function f, use composition of functions to show that f inverse is as given. So if you actually used the 4 steps here, you could get this answer a lot faster. But that's not what they're asking for here. They want us to demonstrate that when you compose the two functions together in both orders, you get the same output as you started with, which in this case would be x. So let's go ahead and do that. So first of all, we need to find f inverse of f of x. So we would write that as f inverse of f of x. Well, f of x is 3x plus 5. And so we're going to plug 3x plus 5 as an input into the f inverse function. And so that's going to be, let's see, this function here, what does it do? Well, it takes the input, x, subtracts 5, and then divides by 3. So I'm going to go ahead and make a shell, and I'm going to plug in my input. And so notice in the numerator, you could drop the parentheses there. You have 3x minus 5. Oh, let's see. I think I made a mistake here. Let me just double check this. Oh, that's supposed to be a plus 5. All right, so we end up with a 5 and a minus 5, so we're left with 3x over 3. And so notice we do get x as an output. So we started with an input of x, and our output was the same value. So we've demonstrated it that direction. What if I change the order of the two functions? One of the things we learned when we did composition of functions is normally f of g does not equal g of f. With inverse functions, that's not the case. They should both be the same. So here we're going the other direction. We're going to find f of f inverse of x. So that's equal to f of f inverse of x. So notice now the input function is our inverse function. So f inverse of x is x minus 5 over 3. So now think about what the f function does here. It triples your input and adds 5. So that's what we're going to do. I'm going to make a shell, tripling my input and adding 5, and my input is x minus 5 over 3. Now to simplify this, notice my 3's cancel. I'm left with x minus 5 plus 5, and so that does equal to x. And so that's how we would show that, and we would use composition of functions to show that these are inverses. All right, now number 12 I would classify as another challenging problem. Again, you'll see one of these in the homework. You're not as likely to see it on a test. So let's go ahead and start the same way. If you want a challenge, go ahead and try it, and then you can see if you were able to do it correctly. So we start the same way. I'm going to plug in fx as an input, so that would be 1 minus x over x. So I'm going to go ahead and make a shell for the inverse function. Notice it's going to be 1 over my input plus 1. So I'm going to make a shell for that. 1 over my input plus 1. My input is 1 minus x over x. So we did a little bit of work with these earlier in the semester, I believe. If not, I'll have to take you back to some old memories. Hopefully you've seen this in the past. This is called a complex fraction because we have a fraction within a fraction. So this is like the smaller fraction, and this is the bigger fraction. So there's a little trick that we can use to simplify this. Look at the fraction, the little fraction inside the big fraction, and there's only one, and its denominator is x. And so there's a little trick we use. So our LCD is x for the little fractions. There's only one here. So we're going to multiply by x over x. And notice what that does for us. In the numerator, 1 times x is going to be x. Now in the denominator, we're going to have to multiply x times that, and we're going to get the x's to cancel, and we're left with 1 minus x. Don't forget, we also have to multiply the other term by x. Basically, we're distributing x times a binomial, which has 2 terms. And so this will be plus x. Well, a minus x and a plus x, that's going to be 1. X over 1 is x. And so we've got that one to work. Our input and output are x. Let's go ahead and go the other direction. So this time the inverse function is our input function. So we're going to plug in 1 over x plus 1. And I'm going to go ahead and make a shell for the f function. That's this one here. Notice if you plug in an input, it's going to be 1 minus your input over your input. And so I've made a shell. Let's go ahead and plug in 1 over x plus 1. Now notice this time our LCD is x plus 1. And that, again, that's our only denominator in the little fractions, this one here and this one here. So we're going to multiply by x plus 1 over x plus 1. Now in the numerator, remember, you're going to have to multiply the 1 by x plus 1 and also this here. When you multiply the 1 times x plus 1, of course that's x plus 1. And then when you multiply the x plus 1 times 1 over x plus 1, you're going to get just the 1. But notice the minus in front, it'll be minus 1. In the denominator, the x plus 1's cancel and you just get 1. Notice this is going to equal x. And that's the end of the video.